Good morning. My name is Julian Podgórski. I'm a PhD student at the Institute of Geophysics of Polish Academy of Sciences. Today I will be talking to you about glaciers and glaciation. And this lesson is the very first one in a long series that is devoted to glaciers, their mysteries, their science, their interesting features, physics, and all kinds of glacial things. We will have a whole cycle of those lessons throughout the incoming year, and this one is the first one. I very warmly invite you to all the next installments in the series. Today's slides were prepared by Jerzy Grzejewski from the same institute, from the Institute of Geophysics, and my job was to translate it to English and deliver it to you right now. Very well, so let's start. The very first thing that we have to mention when speaking about glaciers is the water cycle of the Earth. The water cycle, the one you might have heard about, that the water that's more or less everywhere in oceans, in the atmosphere, in rivers, and also in snow and ice, it's constantly cycling and traveling around the Earth. It evaporates from the seas and oceans, condenses in the atmosphere to form clouds, and those clouds flow to the land, and there, over land or sometimes even over ocean, the water from clouds is dropped back to Earth in form of precipitation. And when it's cold enough for precipitation to form as snow, the snow can fall, for example, in the mountains or in cold areas of the world and just stay on the ground, not melt in the summer. But often it melts, of course, but sometimes it doesn't melt. And for many years of such accumulation of precipitation of snow in a place, a glacier can be formed, as you will see soon. So the glacier's place in the hydrological cycle is the retention of water, the storage of water inland, in reservoirs on land after they fall down from the sky. So that's the first leg of the basics. The other leg of the basics is water itself. What is water? As we know it, water is a chemical compound that's composed of one atom of oxygen and two atoms of hydrogen. And the water in nature, on Earth, naturally occurring water can be found in three different states, in three phases. The steam is when the atoms of water, the particles of water, not atoms, particles of water are rather freely floating in the air. It's not actually clouds or the steam that's going off your kettle. That's the steam that has already condensed on some kind of particles in the atmosphere. And when water condenses because it's getting colder, it moves to a liquid phase, and then there is some attraction between the particles, some atomic bonds between hydrogen and oxygen atoms, between positively charged hydrogens and negatively charged electrons in the oxygen, that make it so that the particles get closer together and start forming liquid. It's still quite loose compared to solid states, but it's much more compact than steam. Then liquid water is what we know as water from our daily life. And when the temperature is getting even lower and lower, the particles of water are forming crystalline structures. Then the particles are arranging themselves in neat ordered patterns of ice. Then they became a solid body that we know as ice. And the third one, the crystalline ice, the solid water, the crystalline ice, is the thing that interests us the most when speaking about glaciers. And this is a physical-chemical graph, diagram, or chart, whatever, that shows those transitions between steam and liquid and vapor, steam and liquid and ice, in a more macroscopic scale, so to say. This time on this graph, we're not speaking about particles, single particles and their interactions. This time we're speaking about what happens to a body of water depending on the pressure and temperature. On the vertical axis, we have pressure. On the horizontal axis, we have temperature. And you can see the red line more or less below the half of the chart. That's around 100 kilopascals. That's the typical pressure we find naturally, the typical atmospheric pressure on Earth. And depending on temperature, within this pressure, we can have different kinds of water phases. Above 100 centigrade, it's vapor, as we know. That's the boiling point at our pressure. If we would want to change the pressure to bigger or smaller, the boiling point would also change a little bit. The below 0 degrees, it's ice. And again, that's the freezing point, and that's something that we're used to. At our pressure of 1 atmosphere, the freezing point is more or less 0 degrees centigrade. And in between those temperatures, it's liquid. So you can see that if we want to have ice in nature, we need to get below this temperature, because even if the pressure would change, the changes in pressure that are known in nature are not big enough to actually move this red line to a place where it would change drastically. Although there are some cases under the glaciers when the pressure actually starts influencing the freezing and the melting point. The next one, and this one is even more microscopic. It looks at the whole world. It's a map that's taken from an old Polish textbook on glaciers, and it shows us how intensive, how much snow cover is found in different places on Earth. Let's look at the equator, at Africa mostly. You can see that Africa is white, it's blank. It means that there's almost no snow cover in those places where it's just pure white. In Africa, in most of South America, in Mexico, in India, or in most of Australia, we don't get any snow at all in winter, in summer, or whenever. Going up or down from equator, we're encountering zones. First zone is in Europe and in the middle of Asia and in the middle of North America. And then going up and up and up, we are having zones which have longer and longer snow cover. So some places, like most of Europe, have only snow cover in winter for a relatively short amount of time, and other places up in the north, in northern Siberia, might have snow cover for most of the year. And in Greenland, in Antarctica, where you can see the checkered pattern, it's the place when the snow cover is permanent. So the year-round, all the time, there is snow cover in the middle of Antarctica and in the middle of Greenland. And besides of this trend of north-south, the farther away from the equator, the more snow, the other trend we can see is that in the mountains, we get more snow than outside the mountains. In South America, the only places that get any snow cover are the Andes. The very tall mountains of South America are getting quite big, quite significant snow cover during the winter. And that's because they are elevated high above the sea level and above the surrounding area. And again, this is how it looks in a kind of cross section. This graph is a little bit unusual, so I'll take a bit of time to explain it to you. The gray shape, the spiky shape, is the elevation. So what's happening here is we took a line along the whole planet, going from the North Pole to the left, to the South Pole, to the right, and looked along this line, looked at different elevations in different places. And going from the Arctic, which is relatively flat with some mountains, there's a tall peak that says that in this place our line goes through Alaska. Then there's western US, which again is a little bit mountainous. Mexico. Below Mexico, there's the drop, that's Central America, or parts of South America. And again, in Peru and Chile, the line crosses through Andes, the very tall mountains, going down and down to Patagonia, which is lower, which doesn't have so tall mountains, to the ocean between America and Antarctica. And in Antarctica, again, we have some notable elevations. And those two lines, the red and blue, show us the snow line. So how far in the mountains you can have permanent snow cover. And the red line is crossing through all those spikes, which means, and whatever is above the line is getting a lot of snow in winter. And we can see that the red line is cutting off the tips of the spikes. So only the tallest mountains in Peru and Chile, the tallest mountains of Mexico and the USA are getting significant snow in winter. But away from the equator, in the Arctic and in Alaska, the red line is much lower, which corresponds to much lower elevation of the snow line, which in turn means that we can have snow in much greater area. And the blue line is the same thing, but 21,000 years ago, during the glacial age, the ice age. And during the ice age, the line was lower, which meant that while nowadays you can get the snow in tall mountains, 21,000 years ago, we were getting snow much lower in the mountains. So on lower levels of mountains, on lower elevation, which translated to greater area of snow cover. In some places, like we could look in maybe Patagonia, the blue line is really significantly below and covers much greater amount of terrain. And how do glaciers form? Since I have told you about the temperature, about the elevation, that's important, but those two things are not everything. The temperature, I think, is intuitive, and the elevation is related to it. The higher we are in the mountains, the colder it is, and if it's colder, it's easier for ice to survive. So the glacier form when three important criteria are met. There's enough snow precipitation in winter. So there's more snow falling than melting during the summer, which is related to the second criterion, that it's cold enough to keep the snow through summer. For example, in Europe, in most of US, in almost all countries, when the snow falls in winter, it melts in spring and there's no snow in summer. And in these conditions, a glacier cannot form, since we want the snow to survive the whole year for glaciers to form. That's why we need a place where it's cold enough for the snow not to melt in summer. This is most often found in mountains, in Alps, and like I told you, in Himalayas, but also in the Arctic and Antarctic, where it's cold enough on all levels, even at the sea level. And the third thing, that's something most people don't think about, it's the relief that allows the glacier to form. Let's look at the image to the right. We have examples of three different mountains, and the one to the left is a mountain that's good for glaciers. It is tall enough to be cold. There is some precipitation. It's tall, so it's cold, and the snow stays for summer. And it has a very nice kind of hole, a niche in it that allows for the snow to actually survive. If we looked at the mountain in the middle, it's actually taller, So theoretically, it should be colder there and it should be easier for snow to fall. But the problem is that this mountain is very steep. And since it's very steep, the snow cannot lie down on it firmly, and it's just falling down to warmer parts of the mountain, melting, and it cannot. And even if it stays on the slopes, when the snowfall comes the next year, the snow becomes so heavy that it falls down instead of staying there and forming a glacier. That's why this mountain doesn't get the glacier. And the mountain to the right is not getting the glacier because it's too low, too short for the temperature to be cold enough for snow survival through the summer. This is the case of the mountains on Iceland and Spitsbergen. The temperatures are cold enough for glaciers to survive even at the sea level, and that's where we get tidewater glaciers that are flowing from the mountains to the sea. And here is a photograph from Spitsbergen. It shows us the case of glacier that's flowing to the sea, and you can see that there's a lot of glaciers in the valleys. The whole valleys are filled with ice. These are it's a quite mountainous terrain with a fjord incising. It's close to the Polish polar station in Hornsund in Spitsbergen. The huge Hansbreen glacier is flowing down from the mountains, and as you can see, it's flowing into the ocean, and it's staying there, although it's receding quite fast. It's moving back. Its front is collapsing into the water. Nevertheless, it is there. It doesn't melt immediately every summer. And you can see more of the smaller glaciers like Tuvbreen and Deilegbreen and Stachelisen that feed the Hansbreen. They're flowing like rivers, like small rivers entering bigger river and making it stronger and more powerful. The same happens with glaciers. The smaller mountain glaciers going down from side valleys are feeding into the huge Hansbreen glaciers, making it even bigger and stronger and carrying more ice. You can also see those black mountains like Tuva and Bergnova and Fuglaberget. Those mountains they have no ice, even though they are taller than the surrounding. So according to what I said before, they should have ice and snow because they're tall and cold. But look how spiky they are. They have very steep and spiky slopes. Whatever snow is falling there is falling down to the valleys when it lands on the glaciers and falls down. If those mountains were flat, for example, we had a big plateau. If we had a big plateau like in the back, if you look at the Tuva-Breen, and behind it, there's a mountain with a hole close to the word Deilegbreen. In this hole, there's also a white spot. It's ice. It's not like those mountains wouldn't have ice anyway. They do have ice and glaciers if only they have a chance to develop one in a favorable relief. And this is a more theoretical, more abstracted scheme of how glacier looks like and what parts does it have. The first thing that comes to mind when looking at this image that the glacier has a quite big slope. It's flowing down, and that's actually what all glaciers do. They are not immobile. They are not static. They're flowing down slope all the time under their own mass, under the weight of the accumulated ice and snow. In the highest part, close to the peaks of the mountains, there's the accumulation area where the snow that's falling into the glacier. There's more snow coming into the glacier from precipitation or from other sources than it's coming out by melting. So this means that every year the layer of snow and ice is becoming slightly bigger, because even though some of it has melted, the new one is more, there's more of the new snow. And as it increases and increases, during the years. We're speaking about long timescales of many hundreds and thousands of years. As the thickness of ice increases, its mass increases as well. It becomes heavier and heavier, and so it's pushing downwards all the ice that's down below, the downslope, and that's how the glacier is flowing down. And as it's flowing along the thick red arrow, it happens sometimes that there are ice falls. Ice falls are not like waterfalls exactly, but there are places where the flow of ice becomes much faster because of, for example, sudden increase in slope below when it's going down an escarpment, and that's where some crevices may appear when the ice is trying to, so in a way, run away from the ice above. There is also on this scheme a tributary glacier, the one I have shown you before on the image from Spitsbergen. That's one of the smaller glacier. It enters the glacier, and the two flow together for the rest of their road down the valley. And the lowest part is the ablation area of the glacier. Ablation area is contrary to accumulation area. In this place, the melting of ice or other ways of losing ice by glacier are stronger than what is brought in by snowfall and by inflow from above. If this is the case, then the glacier is receding and its front is moving back because it's melting faster than it can be refilled from above. If it works the other way around, if the mass balance in this area is positive, then it's more inflow than melting and the front is moving forward. But in the ablation area, there's more melting than accumulation. So all the snow that comes in melts, and in addition, a little bit more of it can melt, a little bit more of ice in this lower part. And anything that can be gained comes from above. In addition to ice itself, that's ice, there's a lot of landforms that are formed by glaciers inside and around. Most common of them are moraines. We can start already up there where the tributary glacier enters the big glacier. A medial moraine is being formed that is made from the material, the rocks, the sand, the gravel that's torn from the sides of the valley and carried down by the glaciers. As the two glaciers meet, all the material that they have brought with them is merged into a stream that's running in between them. In addition to that, there's a lateral moraine that's running along the sides of the glacier, and that's where the flowing ice is eroding the valley around them, as well as there's some content, some grains flowing down from the mountains, and that's carried down as a lateral moraine. And on the front of the glacier, when the long tongue is pushing at the ground, a terminal moraine is found when the glacier is building a ridge on its own. Before the glacier, in front of it, there are also meltwater streams. All the water that's melting in glacier, it has to go somewhere, and it usually goes out through the front, carrying out a lot of this material that was eroded and depositing it in front of the glacier, creating sandur, the large plains of sand, and other different landforms that you might have heard about in school, and hopefully we'll hear about in our cycle. And this is how scientific work looks like in the glacier. The scientists go up to the glacier and dig a very deep hole to look at the different layers of ice. And why would they do this? Look at this. They are measuring things in the glacier, even though at the first glance it looks like just a uniform thick layer of snow. But actually, the scientists know that there's something more to it than just uniform snow, and that it is not uniform actually. Maybe it's not very clear that the layers are not clearly visible on these two photographs, but they are there, and I will now show you how they look in a more abstract way. When the snow is falling on some place, it falls in the form of snowflakes. We all know snowflakes are the nice stars that are light and lightweight and very soft. And when they are accumulating, there is a lot of air between them because of their irregular shape. So they are more or less a loosely packed heap of snowflakes. But with time, when this amount of snowflakes becomes bigger and bigger and they don't melt in summer, the mass of the whole heap of snow is getting big. And the layers at the bottom are kind of crushed and forced down by the layers above. And that's what happened on this black and white image. You can see the first layer of snow being quite loose. They're nice stars. It have a density of around 200 kilograms per cubic meter. Sorry, it's not a lot. It's much less than water. But below that, there are the layers of older snow that have already been compacted both by the pressure of the snow that lies above and by some limited melting that occurs there, and as it melts into water and refreezes, so the snow can melt and freeze again, at least some part of it, not all of it, of course, but some of it. It forms more regular, more granular forms. And the deeper we go into a layer of snow, into a glacier, the more compacted and the more solid is the ice and snow. And at the very, very bottom, when we go down to the actual glacial ice, it's already resembling a solid piece of ice. Like it's very clean. It doesn't have any any structure that would be visible with a naked eye. It's just a solid block of ice. But it was created from those small from those small snowflakes that have been crushed under their own pressure. And in between the solid piece of ice and the loose snowflakes, there is the so-called firn. Firn is the intermediate stage of ice between snowflakes and glacial ice. That is the one that's already quite compact. It's already have very much different structure from snowflakes, from snow, but it's not as solid and as thick as the glacial ice. You can look at the photograph from scanning microscope here. It is firn. You can see those granules, those grains, so to say, of ice. These are the grains of ice that form under pressure from snowflakes. We get snowflakes, they turn into this kind of grains, and those grains are getting pushed even more and more. The air is being pushed out from the whole thing, and they are squeezed into solid ice. This process is very, very different from what we get in our freezers. When we do ice for example, for our Coca-Cola, or we get some ice even on ice rink when we go ice skating, there is a very different process, because then we take liquid water and simply freeze it to the solid form. We go with it below the 0 degrees, it freezes into solid, and that's it. And that's a different kind of ice than what we have in glaciers. Both the firn and the glacial ice are formed in a different way than what we know from our daily life, and so their properties and almost everything about them is a bit or a lot different than the ice we know from our daily life. Thank you for attention for this during this introductory lesson about glaciers and glaciations. The introduction to our course. The subsequent lessons will be more focused on particular either features of glaciers or the methods for studying glaciers, or they will be more focused. This one was quite general and just spoke about glaciers. Its purpose was to interest you in glaciers, show you that the glaciers are really interesting and they have a lot of very, very unusual features, and we will be concentrating on those single things I have been mentioning only in passing in the next lessons. Thank you for attention. Again, I can remind you that the slides were done by Jerzy Giżejewski from the Institute, and goodbye. Thank you.